Alright, so you're probably watching this video to get a start on our gas unit. And that first day of our unit, we actually did things in a little bit of a weird or different way. We started off our day by copying down some simple definitions from this page in Canvas where I posted the PDF version, just a copy of all of the definitions from those first page and then a bit. So you can either go and find that document and copy it down, or maybe just pause as I scroll through this here and copy down what you need to, including doing these example problems where all we're doing is changing our degrees Celsius into this unit Kelvin that we're going to be using for all of our calculations for this unit. Has to be done in Kelvin, not Celsius. So all we got to do is add 273 to this number when it's in C. Just take C plus 273 and that will get you the number in K. So go ahead and go through those, copy that down. The purple stuff is the stuff that I absolutely have to have you writing down. That's mostly the kind of meat of our notes here. Definitions. I did want to kind of draw your attention to some of this standard temperature and pressure stuff though, because I think it can kind of get lost in all the rest of the words on the page, which is why I kind of outlined and underlined things here. This is a really important idea. We're actually going to end up coming back to it shortly. This is our standard temperature and pressure here, and we actually needed to fix both the decimals there. We needed to cross out the 0.15, so that's just 273 like we were talking about before, and actually right underneath it, this kPa, this standard pressure, should be 101.3, not 101.2. So those are our standards, meaning that if we tell you we are at STP conditions, then we're going to be using this temperature as our standard temperature in our calculations and one of these pressures. And I actually like to take a quick moment to talk about those pressure units because they can be kind of confusing. Pressure as a whole is kind of a confusing idea. It's not something where you can really see happening a lot because this is caused by the collisions between gas molecules. So we don't really see it happening. We can just kind of feel it because it is a force. Just like if your parents are pressuring you to go to a specific summer program or take a specific class next year, they're pushing you. They're trying to force you to make that decision. And so that's all that pressure is, a push, a force caused by these gas molecules running into each other and the walls of the container. So think of that when we're thinking about our pressures. How many collisions are happening, or how hard are they hitting each other and pushing on each other? Now, what I was talking about was our units over here, because most of the other stuff that we deal with is only going to have one standard unit we need to recognize. Like volume is basically going to be in liters every single time. We might see it in milliliters sometimes, but even then we're generally going to be converting that into liters for that calculation. So like we wrote down here, milliliters divided by 1,000 will give us liters. Pressure, though, has 4 different units that we could possibly see and use in our calculations. So we need to be able to recognize each of them. And this kind of tells you how to pronounce or say each of them. But more than that, I kind of want to help you understand what they are and where these weird sounding units come from, because they do kind of seem random. And I think the best way to understand them is to kind of look at them in the context of this standard pressure. So our standard pressure is our normal pressure that you, me, everyone is under. It's the average pressure here on Earth. And this first unit that we use, ATM, which stands for atmospheres, was actually a unit that people made up just to make the math simpler and to help make the numbers make more sense. Because at any given point in time, we have a full atmosphere of gas molecules pushing in on our body. That's the air pressure. Then that, and caused by those collisions between all the molecules in the whole atmosphere, they said, okay, well, we're under 1 atmosphere of pressure. Just 1 full atmosphere of gas molecules pushing in on us is how much pressure there is. So that makes it really easy to compare things to each other, because if we do a calculation or something and figure out, oh, the answer is 2.5 atmospheres. Well, that's 2.5 times more pressure than we're normally under. Or if we do a calculation and it ends up being 0.5 atmospheres, well, that's half a normal amount of pressure. So atmosphere is a really nice, clean unit. Plugging 1 into equations is scientists' favorite thing. It just makes it nice and simple and shows the basic relationships. So people came up with this unit and made this unit. They're like, how about we make up a unit that's nice and simple, so that people can understand this pressure thing better. And that's where atmospheres came from. It's just contrived to help people relate better to these numbers. Technically, kPa is our standard unit for pressure, just like meters is our standard unit for distance. We don't measure everything in science in centimeters or feet or inches. Our standard is meters. So technically our standard for pressure is kilopascals, these kPas here. But the numbers just aren't quite as nice and neat as with atmospheres. So while we use it when we have to have things standardized, it's not quite as easy to relate to. So then we have one of the weirdest sounding ones. mmHg stands for millimeters of mercury. Now, mmHg in millimeters of mercury already looks and kind of sounds a little bit weird, but the weirdest thing about it, if you actually think about it, is that for whatever reason we're measuring pressure with millimeters. Those are those itty-bitty little lines on our rulers. They're teeny tiny, and rulers measure distance, not pressure. So it doesn't seem like it'd be a pressure unit, and it kind of confuses a lot of people when they see it. But where that comes from, I've made a little space here just to kind of show you, is actually ancient Greece. Back in the day, before we had technology, ancient Greeks could feel air pressure changes, but like we were just talking about, they couldn't see those changes. And so they were trying to figure out what was changing and trying to measure things in order to quantify the amount that things were changing, even before they had any kind of technology. And so they had to use some pretty simple equipment. And that's where these units came from. The first thing that they needed was a really long, skinny tube that was closed on one end but open on the other. And then they put that tube open side down into a bowl that was filled with mercury. So a really shallow bowl, but with plenty of mercury there to fill up the tube if it was so inclined. But as you might suspect, just like with a test tube, if we turn a test tube upside down over some water, it's not just automatically going to go up into the tube. It's just going to sit there underneath the tube. It needs something to push it up into the tube. And that's where air pressure comes in. And that's how this measures air pressure. At any given point in time, like we said, our molecules in the atmosphere are moving around in all different random directions, pushing on each other, and everything around them, including the surface of that mercury. And as that pushes down on the surface of the mercury, then the mercury is pushed up into that tube. It goes into the tube, and the more air pressure that we have, then the higher up in the tube the mercury was forced. So back in the ancient Greek days, they actually measured how many millimeters up this tube the mercury was forced on any given day, and that told them whether it was a high pressure day because it went really high in the tube with a lot of millimeters of mercury, or on low pressure days it was lower down where it was only a few millimeters of mercury. So really old-fashioned technology, and the units have just stuck around. We still use that to this day to measure air pressure. Now, the last pressure unit that we have written here is PSI, and as it tells us, PSI stands for pounds per square inch, and this actually isn't going to get used very much in our calculations, but I do like to tell people, because this is what you're going to see pressure measured in here in the US. And so just to give you an idea of what this standard pressure is in, normal people units, if you go down to the car store or have to pump up your tires or a basketball or something, it's going to be in PSI. And so standard pressure, your normal pressure that you're under at every given moment, is 14.7 psi. And I actually really like to kind of talk about this briefly, even though it's a little bit of a distraction, because at every moment of your life, you have that much air pressure, those molecules pushing on you that hard on your skin every single moment. And that's about 15 psi if we rounded it. And think about 15 pounds per square inch. Imagine a 15-pound dumbbell, or if you have one at home, go find one and put it on your hand. Like, it's probably a little bit bigger than a square inch at that end, but that's a lot of pressure pushing in on your hand. You probably won't want to leave it there for very long. And that's the amount of pressure constantly pushing in on your skin, every inch of your body at every moment of your life. The only reason that you're not crumpled down and in pain is because we have internal pressure, like blood pressure, that's kind of balancing that out and pushing back against it in order to make sure that we can still live underneath this immense pressure. So those are all of our pressure units. Make sure that you did a quick definition for volume down here. We already pointed it out, but it's really important for the next chunk of information that we know what volume is. It's just the amount of space that things take up. And then on this first page, I'm just going to real briefly kind of skim over some of the important stuff from these definitions. Hopefully you can recognize the words expansion and compressibility, just expanding and compressing, meaning spreading out or getting closer together, changing our volume. Density you've probably learned about before. It's a measure of how compact things are, and the reason we're talking about it here is because gases all have very low density. And gases are also fluids, not liquids, but fluids. Both liquids and gases are fluids because they can flow. So we can pour gases just like we can pour a liquid. We just can't see it and interact with it quite the same way, but it is still a fluid. And then these last two words, it's actually really important that we talk about them and you understand the difference between them, because these two words I can basically guarantee are brand new to every one of you, and I can also basically guarantee that they are going to show up. One or the other of them will show up on your test, so you need to know the difference between them. Diffusion or diffusion is about the movement of particles from high concentration to low concentration. And what I remember that that's diffusion is that there has to be a difference in concentrations. We have to have high and low in order to have diffusion happen. And you see my little green note that you may or may not have decided to write down there. But this kind of comes back to that idea of he who smelt it dealt it. Wherever that strongest smell is coming from, probably the first person to smell that smell is probably pretty close to where it came from. So if I spray perfume here in the corner of my classroom, everyone in the classroom eventually will be able to smell it. But the first people to smell it, and the people that are going to smell it the strongest with the most kind of smell molecules in their noses, are going to be the ones closest to me where I was spraying that perfume. So diffusion is movement of particles based on a difference in the concentrations, from high to low concentration. Effusion, on the other hand, is about our gas molecules still moving, but it's all about them escaping. Once again, effusion, escaping, just like we had our diffusion happening when we had, let me get a better color here, diffusion when there's a difference, effusion happens when our gas molecules are escaping. Just like if there's a jailbreak and our prisoners are escaping, they're not walking out through the big wide open doors and the big wide open gates. If they're escaping, they're probably squeezing through a small hole. And that's the key with effusion, is our gas particles have to be escaping through a really tiny hole in order for that to be effusion. So that's why I use the word escaping there. It could just be moving, but the word escaping always helps me remember that small hole is our effusion. Now, this kinetic molecular theory thing is a little bit maybe boring sounding. It's just a lot of rules that our gases have to follow, some basics that we can count on in order for all the rest of the stuff that we're doing this unit to work. So we defined later that ideal gases are gases that obey the rules of kinetic molecular theory. So that's all that this really is some rules for gases that let us do what we need to do with our gases. The most important things to kind of remember or recognize is that gas particles are super duper small. Can't see them, and there's huge distances between them. That's that low density idea. And these molecules are constantly moving in straight lines. They're never going to be curving around, spiraling around, because these gas particles don't have any forces of attraction or repulsion between them. So the only thing that's making them move is the energy they have. In fact, we're going to talk about how that energy is really the temperature of our gas. And once they get started moving, they're going to go in a straight line until they hit something, and then they're going to bounce off in a straight line. They're not attracted to anything, so they're not going to bend towards or away from anything in between those collisions that it has. And when things collide, there's no energy lost. So nothing's going to be speeding up or slowing down overall. The whole average speed of all the atoms in the container is going to be the same, so that overall we have the same amount of energy there. That's what we call elastic collisions, although you'll worry about that more in physics. So, this last idea that I kind of referenced real quick is that kinetic energy, the movement energy of these gas molecules as they're moving around, is only dependent on the temperature of the gas. When you feel like a balloon that's full of gas, you might feel that it's hot or cold. But when we're thinking about and measuring gas molecules individually, or trying to figure out whether they're hot or cold, if we're looking at those individual gas molecules, we can't actually measure the temperature of a molecule because it's too tiny. So that temperature that we're trying to measure or observe is going to be reflected by the speed or how fast that molecule is moving. Just like if you rub your hands together, the faster you go, the more energy you use, the hotter it gets. It's just because your particles are moving faster and faster and faster and helping to warm up and speed up the ones around it so that you're feeling as heat. So heat 'em up, speed 'em up is a nice simple way to remember that. And that kind of brings us into that definition of temperature. Measure the average kinetic energy, because kinetic energy is temperature. So, we already kind of touched on these Kelvin conversions. If you were wondering if you got them correct, let's go ahead and show you those answers here. If you didn't quite get them correct, let me know and let me help you understand what's happening here, because we're going to be doing a lot of these temperature conversions. This is just kind of step one before we plug numbers into the rest of our equations and stuff. So let's go ahead and move on to those graphs that we've got here in the middle of page 2. In these graphs, what we were going to focus on is how that pressure, volume, and temperature that now we understand are changing each other. So as one of them changes, how does it affect the other one or two? So what we're going to be writing here is just those simple P, V, and T letters to represent pressure, volume, and temperature, of course. And we're going to say something, and I'm just going to use X and Y as an example. You do not have to write this down. That like X up, Y down. And that's a shorthand abbreviation telling us that as X increases, Y will decrease. But it's 4 letters, 4 symbols there, instead of having to write out a full sentence. So we'll be able to kind of summarize some important relationships that we need between P, V, and T with some simple kind of shorthand like this. So I'd like to help you reason through this. And the most important thing to remember as we're reasoning through this is that our pressure is all about collisions. Our volume is about the amount of space that things take up, and our temperature is about how fast or slow things are moving, the speed of those gas molecules. So those are the 3 things we need to kind of keep in mind as we are talking about how these things will change each other. So first, at constant volume, so here our volume is not going to be changing. If you look at my axes, temperature is on my x-axis, pressure is on my y-axis. So those are the 2 things that are going to be changing. We're going to leave volume alone for just a second. we're going to try and reason through, if I increase the temperature, what is going to happen to our pressure? And while we could talk about gas molecules here, sometimes people struggle to really understand what gas molecules will do. And so I kind of like to tell people to think about gas molecules like kindergartners. They have feelings and thoughts, and they're kind of, almost sort of, you can imagine that they're people or going to be people, but they're not really. Right now, kindergartners are just little balls of energy and hopefully fun, but sometimes a little bit of misery along with it. So you can definitely tell I was not meant to be a kindergarten teacher. But regardless, let's think of these like kindergartners. And I tell my kindergartners to increase their temperature. My gas molecules are increasing temperature. That means that my kindergartners are increasing their speed. What is going to happen to the number of collisions? Let's say we're in gym class or something, and I tell my kids to start increasing their speed, speeding up, run faster, faster, faster. Are there going to be more or less kindergartners running into each other? And hopefully, if you think about this, there's going to be more and more kindergartners hitting the wall and each other if we tell them to start running faster and faster. On the other hand, if I tell them to slow down and decrease their temperature, decrease their speed, then the number of collisions between kindergartners or gas molecules should also be decreasing. Honestly, that's one of the first things that I hear people saying about elements is just walk, slow down, just walk. Because we don't want them running into things constantly everywhere. So, the relationship is true whether it's kindergartners or gas molecules. All I really need you to do is write one or the other of these, because of course, if they both increase together, they'll both decrease together. But I do kind of like to see and write both of them down, just because it covers every possibility. And from there, we can tell that this is a direct relationship because our arrows are going the same direction, no matter they're up, up, or down, down. And because of that, the graph that we can draw here between pressure and temperature is going to be a nice straight line, kind of an x equals y looking graph. And technically, in real life, if we did a lab and we graphed the data from it, it might be steeper or shallower, but no matter what, it's always going to be a straight line with a positive slope. So that's all we got to do there for that first set of variables. Through this next graph, we're going to be talking about how pressure and volume are going to change with each other. So let's imagine our kindergartners are in gym class again, and instead of being in the gym, we decide that, I don't like how much people are running into each other. Let's take them outside onto the field and let them run around instead. If we increase the volume of space that our kindergartners can spread out in, then what's going to happen to the number of collisions between them? Well, hopefully you can realize that less students, less kindergartners should be running into each other if they have more space to spread out in. So, as volume increases, our number of collisions, our pressure is going to decrease, and our gases will do the same. On the other hand, if we decrease the volume, if gym is flooded or we can't have class in the gym, and instead we have to try and have gym in a normal-sized classroom, then our number of collisions, if we try and keep moving at the same speed, that constant temperature, then the number of collisions happening between kindergartners is going to go way up. Notice that these arrows are going opposite directions. So this is an inverse relationship, and our graph is going to head the other direction. It is going to have a generally negative slope, but it is going to have a little bit of a curve in it towards that origin. It's going to curve down and then over. Now for our last relationship with our volume and temperature changing, let's imagine that our temperature is increasing, meaning our kindergartners are moving faster and faster. So we've taken them to gym class, and let's say we're starting off on the field in a big wide space, but we're starting with them really close together. We're giving everyone instructions and talking in a group, so everyone is all in one spot. As I start telling the kids to start walking and increasing their speed a little bit, what do you think is going to start happening to the volume, the amount of space that those kindergartners take up? Probably going to be a little bit more space than when I was just talking to them in a group. And if I told my kids to start running around, then they're going to start spreading out even more, taking up even more space. So if we increase the temperature of a gas, the faster molecules are going to start spreading out more and more. So as temperature increases, volume increases with it, and if temperature decreases, then volume will decrease with it as well. Hopefully you recognize that this is a direct relationship because our arrows are going the same direction again, which means once again, this is going to be a straight line graph. So at this point, these are actually our first really important ideas, our first gas laws of this unit. And even before we get to those calculations that we are going to do at the bottom of the page, we actually have a worksheet for you to practice and do here, just with these general relationships, where we're going to be drawing some more of these letters and arrows, and those will be our answers. But it's really important we do this step because it's going to help us with all of the other equations and things as it gets more complicated later on. So let's go ahead and look at worksheet A together. Here, what I'm asking you to do is interpret each of these situations and label which two variables are changing. Remember, we're always choosing between pressure, volume, and temperature. And then we're going to be saying whether those are increasing or decreasing. But it's not necessarily going to spell it out for us, so it's part of that context clues, reading comprehension skills, to really dig into understanding what's happening and kind of pulling out the gas laws that are happening here. So in number 1, it says that a football inflated inside then shrinks outside on a cold day. If we're thinking about our 3 variables and which of them we are most confident is changing here, what words are kind of our key words telling us that either pressure, volume, or temperature are changing? Well, I'll tell you, in class, most people were most confident and keyed in on this cold day here, either because it was the end of the sentence or because cold all the time reminds them about temperature changes. And so temperature here is one of the variables that is changing. And of course, a cold day means that that temperature is decreasing. So that's half of our answer there. What we need to do is find out whether it's pressure or volume changing with our temperature here. So we're looking for some more key words. And it's talking about how our football was inflated and then it shrinks outside on a cold day. So these key words are talking about how much space that football takes up. So hopefully you're realizing that volume is what it's talking about changing. Although this seems counterintuitive because it's talking about inflating, which sounds like it means more volume, and shrinking, which sounds like it's talking about less volume. But you need to make sure you're paying attention to where the change is happening. The change that we saw in our temperature was when we took it outside on a cold day. So which of these changes is happening when that temperature is decreasing? It's that shrinking, that volume decreasing. Hopefully, if you flip back and check in your packet, you'll notice that we had just finished up talking about how if temperature goes down, volume will go down with it. So that is our answer here, just V down, T down. And it doesn't matter what order they're written in, or even where they're written, as long as I see those 4 symbols together in this space. So you could have written V down after T down. It doesn't matter whether it's before or after or where, as long as they both get there. Now, hopefully, you would have realized if you had tried to say, oh, the football was inflated, V goes up. You need to go and double check anything that you write against the gas laws that we just had, because V cannot go up if T is going down. That breaks the law, so that can't possibly be happening. I must have been misreading something because that wouldn't be true. So this is V down, T down, here to start things off. As you look over the next few examples, some of them are a little bit easier to figure out. Like this one talks about pressure will be higher when the car is traveling over hot asphalt. It's really spelling it out for you there. All the way down to number 8, which is kind of mysterious here, talking about just heating a sealed can. But each of these has enough information for you to reason through what's going to be happening. It's important that it's being heated, but it's also important that it is a sealed can. Think about how a sealed can either can or cannot change, and that will help you find your variables and how they might be changing here. Number 4 is probably the one that confuses people the most. It's probably the least specific about what's happening. And so I would recommend, if you're not quite sure what's happening in the upper atmosphere, where there's fewer gas molecules, sure, that might be useful. There are some other questions in here that talk about very similar things. Going up in the atmosphere is very similar as going up in the surface of the ocean or going to a high altitude on a plane. So some of these other situations might help you reason through some very similar situations there. But it's all about context clues here and reading to understand some of the words that are telling us about these variables. So I just need you to finish out these next 7 examples with just a letter and an up or down arrow, another letter and another up and down arrow. If you have any questions at all about these, please come in and ask for help, and I'll help you get there.